Everyone, can you hear me?
Yes, sir.
Okay, so are there anyone who is yet to join, or all of you are present here? Any of your friends are waiting or will join today? Let's wait for 1 or 2 minutes. We can start. Yeah. So by the way, have you gone through the problem that I told yesterday? I mean, in the last class, a very simple perturbation problem.
Yes, yes. The answer should be in n. The answer contain n.
And answer will contain.
In the value n.
Yes, that can contain, of course, because n is a parameter in the
Yes, yes,
problem,
yes.
so that can contain n also. So have you done it?
Yes, it is dependent on n. The
Yes.
first order correction.
So what is the correction to the first order energy for the zeroth? I mean, for the uh, n equals to 1 state. Have you got?
N. I mean, I am generalize it. I didn't calculate for n is equal to 1. Uh,
So you just put n equals to 1 in your expression. Nothing more.
okay, then I have to calculate it. I have the expression. I have to
So is it
solve.
too much complicated? I mean, I hope the integral is not too much complicated, right?
No, no,
What
no.
do you think?
Integral is general. It is like previous. We have done it.
Yes, yes. So it is a finite limit integral, right?
Yes, yes, yes.
So from, I think, from how much? From point two, or what was the number? 0.3 to 0.6 or something like that, no?
0.2 to 0.6.
Yes, 0.2 to 0.6. So the integral is only from 0.2 to 0.6, right? That is the
Yes, yes, yes.
procedure, right? Yes. And what is the integrand for nth state, let's say?
So the answer is approximately zero point 0.4 epsilon, I think, for first order correction.
For which n?
N is equal to 1 for n is the
Yes.
first,
So
I
so
guess.
so okay. So let's just check it in a way that everyone can understand. So what is the integrand besides dx? What is the integrand? The
For
integral
cos
is from point two to, sorry, 0.3 to 0.6, right?
zero point 0.2 to 0.6.
0.2 to 0.6, and the integrand.
Integrand is a cos zero point 0.4. It's complicated, like
So what is the nth energy eigenstate of a function?
root under 2 by L cos n pi x by L, sin n
So
pi
that
x by L.
that is the psi n, right? Psi n zero.
Yes, 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 yes.
Yes, I mean subscript zero. Sorry, superscript zero, right? So that is the psi
Yes,
n
yes,
zero.
yes. Yes.
And what is the perturbation?
Epsilon.
Epsilon. So epsilon comes out of the integral because it is a
Yes, yes,
constant,
definitely, definitely.
and the integral is only zero point 0.2 to 0.6
Sin
root of.
square n pi x by L.
Yes, so it is from 0 to L. Yes, it is sine square parallel, and there is also a 2 by a factor outside, right?
2 by L factor outside.
And the integration should be done from, not from 0 to L, but from 0.2 L to
0.2 to 0.6. 0.2
0.6
to
L, right?
0.
Yes. So whatever is the answer is the answer. Of course, it will not be this one dependent on. It will depend on n, of course, because there is an n, and if you integrate, there will be different n factors coming out if you do the partial integration, right? That
Yes,
is
yes,
the
yes.
usual. Yes. So the process should be clear to all of you. The integration is very much easy because the perturbation doesn't depend on the space x, and it only depend. It is a constant perturbation because the picture I had drawn, you see, from point 2 to 0.6, there is a constant perturbation which has a value of epsilon. So the epsilon comes out of the integral, and the integral is nothing but 0.2L to 0.6L sine square n pi x by a, or let's say L whole squared dx, and there is outside 2 by a, which comes out as squared of root over 2 by a and an epsilon. Is that right, Shovik?
Yes, sir. That's it.
Yes. So if you put the value of n to a specific number, you will get the specific in correction to the specific in energy eigenvalue. So very good. So this is the usual procedure that you should do. This is the integral is easy, but of course you have to put the values of 0.6 and 0.2 wherever possible. So anyone having problem with this, facing difficulty in this problem, or any other thing, other derivation that I did yesterday? Because we will be using this today also. We will today do the second order correction, and we will not go too much because these are recursive things and we can do it recursively. So nobody does it by hand, everyone does it by writing proper programming code. So anybody facing any kind of difficulty regarding yesterday's perturbation part? We can discuss for a couple of minutes, or if there is no such case, we can start directly. Okay, so let's share my screen. So is it visible? Is the screen visible to all?
Yes, sir.
Okay. So what we were doing was, so I think today the number of students present here are more than yesterday, right? So some of you might have missed. So am I correct, or everyone got the notes? Probably I forgot to upload the notes earlier. I did it just after getting your mail, one of your mails. So have you gone through this perturbation theory by yourself, or you understood from your friend? For those who have not been able to join yesterday, so did you face any kind of difficulty regarding this? Because while I
Sir,
was
we record the class every day. There is no problem.
okay, so all of you recorded, right?
Yes,
You have
yes,
the recordings.
yes.
Okay, fine. That is excellent. Okay, so then we can start with the perturbation theory second part. So today what we will do, we will see, so our aim is to calculate the energy correction of second order. This is important. So why this is important, you will see. Because let's say your first order correction becomes 0. So it happens. So let's say, so okay, so how to okay, so you have done all the I mean you have derived all the eigenstates, generalized eigenstates using n for the harmonic oscillator potential. The derivation or the problem you have solved, how to find the eigenstate of nth energy eigenstate. This was done in the previous semester or course. So maybe one of you can answer. If not, then also it is okay, but that will be easier for me to describe if it is so. So harmonic oscillator nth wave and
Yes.
yes. Yes, can you please repeat? I couldn't hear you. Can any of you please say that whether it is done or not? The full set of eigenfunctions for harmonic oscillator potential.
Yes, sir.
So So that was done, right? So what is the parity of harmonic oscillator potential? I mean the eigenstates of the harmonic oscillator potential. So by parity I mean that what is the nature of the solutions. So
n equal to 0 তে ইভেন আর 1 এ অড তারপরে ইভেন এরকম ভাবে।
yes, so first one is even, then is odd, then is even, then is odd, right? So this is the usual characteristics of the. So what happens is that if you have a linear perturbation, so let's say your perturbation involves, let's say, epsilon x, instead of constant you have same formula for the first order correction, energy correction in case of harmonic oscillator. You will see that the odd, the even eigenstates, which are even functions. So if the perturbation is present from minus infinity to infinity, let's say it's very small, so you will see that the perturbation formula that we got yesterday will give you 0, because an even function, if you square it out, then also you get the even function. And interesting thing is, if you have odd function, then also you have to square it, because the formula that we derived yesterday involves a psi n, and the h part is in between, so you have psi n squared h, so h prime. So h prime, let's say, is linear. Let's say it depends only on epsilon into x, so epsilon comes out of the integral and x, and you have psi n squared. So any even or odd function, if you square it, you will get an even function, and eventually your integral will become 0. So the first order correction to any kind of this thing will be 0. So then you will get 0 correction to energy up to first order. So in that case you have to go up to second order, and this is important because in certain scenarios the second correction is the first correction to the energy, because your first order correction is 0 out of the integral. So that's why the second order is also important. So just to recap a bit for those if you have not gone through, or probably could not make yesterday's last class. So we are doing this perturbation theory. Of course the perturbation is time independent plus non-degenerate states. Non-degenerate energy eigenstates. This is not the ultimate form, but we are doing a simpler version of the perturbation theory. So the perturbation we consider is time independent, and we are dealing with a system which has non-degenerate energy eigenstates. So there is only one wave function, one and only one wave function for every eigen state. Okay, so what we did previously was we consider that the total Hamiltonian is, let's say, h naught plus lambda h prime. So this is the perturbation. This is the perturbation, and of course, as it is a perturbation, lambda has to be less than 1. It is a very small number. So what we do is that, so previously we have analytical solution. That the unperturbed state has this kind of energy eigenstate with En0 psi n. So the notations were introduced previously, so if I miss something, please let me know that I am not following the previous notation. Okay, so to me the subscript is the correction, and the lower, I mean the superscript is the correction, and the lower index n, this is the nth eigenstate. So we have this analytical solution. Okay, and we want to find what is the solution to this. So there must be some kind of this, and we have En of psi n. So these they do not have superscripts, which mean that they are the actual solution of the system, including the perturbation. So what we did was we expanded En in terms of the known things. So this is En0 plus lambda En first order correction. Maybe I will forget some of these brackets in the superscript, but I hope you can understand this. So this is nothing but, let's say, sum over j lambda j en j. Sorry, this is lambda power j, and this psi n, this is the wave function of the actual system, is nothing but the unperturbed one plus first order correction plus second order correction and so on, which we can compact in a compact notation. We can write it as lambda to the power j psi n j. And by matching, so by matching the lambda to the power 1 equation, we got the corrected energy eigenvalues for the first order is nothing but the inner product of psi n with h prime and with psi n 0. So this was the energy expression for the first order correction, and to the second order correction, this is psi n 1. This involved m, but we do not take this nth energy eigenstate. Psi m 0, this we can write because the energy eigenfunctions for the analytical solution forms a complete basis, orthonormal basis, as you all know, and this comes out to be sum over m not equals to n psi m 0, and this becomes psi m 0 h psi n 0 en 0 minus em 0. So this was the expression. I hope I have done it right. Okay, so let's put it a box here so that we will need it whenever we want. Yes, fine. So I will start today with the second order equation for so by matching the second order lambda squared equation. So if you remember the, okay, so probably messed things up. The lambda squared equation. So the lambda squared equation was h0 psi n 2 plus h prime psi n 1 equals to en 0 psi n 2 plus en 1 psi n 1 plus en second order correction psi n 0. So this was our usual expression. So you have to somehow do whatever you want and somehow get rid of all those unnecessary things and find out what is en2. This is our required quantity, this one. So we do the previous trick. We multiply with a bra vector both sides. So what we will do, so multiply both sides by psi n 0. So let's see what we get. So this becomes psi n 0 h 0 psi n 2. Please correct me if I am wrong, because the screen is small, so I cannot see what I am writing from the previous line. I have to somehow rely on my notes. So this En0 is a constant, and it becomes En0 sin2 plus En1 sin0 sin1 plus En2 sin0 sin0. Now, can someone tell me what is this value based on the previous derivation? Can someone tell me what is this value? Anyone have gone through the derivation?
So 0.
Yes. So why 0? Yes, you are absolutely correct. But why 0? So Ayandeep, if you face any kind of language
Sir,
barrier, don't feel shy. Okay. So you are comfortable in your own language. I am also comfortable with whatever language you are speaking to till now. So don't hesitate your answer. Okay. So go on. So why it is 0?
sir, I am not actually. I am actually not go through the note of the previous day, but
Okay.
I
So what told you that it is 0? So you do not have to go through the derivation, but if you remember a certain thing, you can answer. So you do not have to calculate line by line. So your answer is absolutely correct. But why it is 0? I mean, only one specific thing makes it a 0, right? You also know that. So what is that thing? Anyone wants to comment on this or have done this? Yes.
Orthonormal states there.
Yes, so psi n1, the first order correction to the wave function, psi n1 involves which states? So previously we had written, right? So this psi n1 contains all the states except n, right? You see, the sum is over m, but it do not include the n. So, and we know that the psi n0, the unperturbed energy wave function eigenstates, are orthonormal to each other, right? So it would have given you a finite number if this psi n1 contains psi n0, but we know that we have explicitly avoided it. So that's why this is 0. So all of you are correct. This is 0 due to the fact that psi n1 do not contain psi n0. Okay, fine. So now let's continue with this. So H acting on this will pull out a En0 and will give you psi n0, psi n2. Fine. And this plus psi n0 H prime, and is we split m not equals to n, and we had all the cm's. So cm's are nothing but like this. So this is, so what I have written here, m0h. Okay, so m0 h prime psi n0 en0 minus em0. So this was the cm, and we had psi m0 get. Okay, fine. And then in the right hand side we have en0 psi n0 psi n2 plus our required part So this psi n 0 is 1, right? Because they are orthonormal eigenstates. Okay. And now you see there is a cancellation in the left hand side and right hand side. So this cancels with this, and we are left with something which we want. So this is en2 equals to sum over m not equals to n. So this we can pull out of this thing outside. Psi m0 h psi n0, and the rest thing is psi n0 h psi m0. So what is this? So this is nothing but the mod squared, right? So this is en correction second order. This is nothing but m not equals to n. Okay, so I missed it somehow. So you should remember me, right? This is en0 minus em0. Then we have en0 minus em0, and these are the same things, but they are complex conjugate of each other. So we can write it as psi m0 h prime psi n0 mod squared, right? So this is the correction that we want to do. Okay, so maybe this is fine. So this is the energy correction to the second. So this is the second order correction to the energy eigen value. So this, I hope this is clear. So you can also do it yourself. You just multiply with psi n0 and rely on your previous day fact that psi n1 contains only contains all the states except psi n0, and you will be able to do. There is nothing much exercise, but the important thing is that we found that the correction to the first order in energy eigenvalue is something which has a proper analytical form. By analytical form, I means you do one integration and you find all correction up to first order energy in the energy eigenvalue. But this is not the case here, right? So in this case, this sum goes from m equals to 1 up to infinite because there are infinite eigenstates in this case, but excluding n. So in order to find out what is the correction to the second order energy eigenvalue, you have to do this integration and you have to sum those up for infinite number of times, which is practically impossible. So but you cannot ignore any one of the terms, see, because this thing every term contributing to this summation, so of course there is a summation over m, every term contributing to the summation is equally important. So you cannot do, let's say you want to find out the correction to the, let's say energy eigenvalue of the 10th eigenvalue 10th eigenvalue energy. So you have to sum from 1 2 3 4 5 6 7 8 9, then 11 12 13 14 and so on and so forth. But you cannot cut to any value, because every possible integration which contributes to this sum is equally important. So this is series, you cannot truncate anywhere, so that will give you a wrong result, or you will overestimate or either underestimate in the correction. So it would be nice if you have some kind of compact expression like the first order energy correction, which you have to do only one integration and that's all. In this case, that is not the case. So this is the energy, this is the difference between these two correction in energy eigenvalues. So what now I will do is that before moving on, I will say that the energy eigenstate correction, so this psi n2, that also can be done using this procedure. You have this lambda, this one, lambda squared equation, and you do all those things which you first write what is the wave function in terms of orthonormal eigenstates. You first take all of them, and you will see that some of them are not necessary, because if you add them, even if you add them, you will not get any 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 new result that we got yesterday. The derivation we did yesterday, you will not get any new result. That's why that was the main reason for leaving out the psi n0 out of psi n1. So you will do this, and you will find that this also has the same expression, but it is too long and very much complicated. But the procedure is same. You first write psi n2 in terms of all psi n zeros. So before moving on, I would just like to do this. So this is a problem in perturbation theory, that you, in order to get a very much correct result, you have to add possibly infinite number of states. So if you are in a harmonic oscillator, you know that n is unbounded from above, right? So n has a zero value. If you are in the harmonic oscillator, so n has a zero value, that is the ground state, and it goes on and on and on. So there is no upper limit to n, and this summation tells you that you cannot cut to some point of energy eigenstate. So you have to do and possible infinite sum, but that is too much for this second order correction, and we are not only up to very much high order in perturbation theory. Let's say you are calculating the 10th order correction, so that will be small. We know that will be small, but this is only the second order correction. And as I had said, that your second order correction may be the first non-zero correction to the energy eigenvalue in certain cases. One such example is harmonic oscillator. With linear perturbation, you will get zero correction to the energy eigen value up to first order. So it would be nice if we can somehow reduce this summation to something concrete, which is finite. I mean, which is finite means we have to do finite amount of calculation to find out what is the correction. So the next step is to reduce this equation in such a way that you can possibly calculate what is the value. So this process of transforming this sum to a finite thing was done by two experts in this field. One is Dalgarno and another is Lewis. So this method is known as the Dalgarno-Lewis method. So this is Dalgarno-Lewis method. So this is the Dalgarno-Lewis method. Okay. So the main thing, so our aim is this: we want to simplify this en2 expression in such a way that instead of doing infinite integrations and adding them up, which is practically impossible, we want to calculate it in a finite amount of calculation. So we will try to figure out what is the way out. So first, starting with this, so this method starts with an if. So if you can find an omega. So omega is nothing but a function. If you can find an omega which respects such thing, h prime, the unperturbed thing, and this one, which is nothing but h0. So omega is a function which has a same footage with respect to h0. So if you can write an omega which is a function and which can act as a commutator with h0, and if that can represent your perturbed Hamiltonian, so the h prime, if it can be written as the commutator of omega and h0, then this is possible. So then this energy, second order energy correction, which is a series now, can be approximated, and in an exact manner it can be written in a finite form, which I am going to do now. So there is an if. So probably you have to find this omega first, and then you can solve what is the correction to this. So we first start with an if, that let's say we have an omega which behaves in such a way that it is a commutator with H0, and your perturbation and perturbed Hamiltonian can be written in this form. Then you can simplify. So now this is straightforward. So we start by writing En2. En2 is sum over m not equals to n 1 by En0 minus Em0, and there is a mod square, so I can split it up. This is psi m0. So let's see what I'm doing. Yes, so this is psi m0 h prime psi n0, and the complex conjugate of this thing psi m0 h prime psi m0. So this was our previous thing. So this is a summation, and we will see how this summation can be taken care of. So what we do, we replace one of the h prime by whatever I have written over here. So this is 1 by En0 minus Em0. So I replace psi m0, and I have written it omega h naught minus h naught omega psi n0, and I leave it as it is. Psi n0 h prime psi m0. Okay. So then what I have to do? So then your calculation will do it by itself. You will not have to do something. So this h will act on psi m0, and okay, so let's write it over here. So what it will give? So it will give, let's say, so psi m0 omega h0 psi n0 minus psi m0. So you have to be careful, because these are they're commutators. They're not just functions that you can interchange. So these are commutators, and in matrix notation, you know that two matrix in general cannot commute. They can commute, but in general cannot commute. So that is very much possible. So you have to keep in mind that these are actually matrices. So if I mess things up, please remind me. Psi m0. So this will act on this will act on this. So what it will give you, there is a psi en0 minus em0, and so the first term is en, it is a constant, it comes out of this thing, psi m0 minus, okay, sorry, psi m0 omega psi n0 minus, and this will act on this, you will get en0 psi m0 omega psi n0, and this thing is as it is, psi n0 h and psi n0. So you see, you can take common, and this factor can be cancelled. So probably you can get, but I am cutting it like this. So I hope you can understand. So there is a sum over m not equals to n, and then you have psi m0 omega psi n0, and from here you have psi n, I forgot the 0, psi n0 h prime psi n0, right? Okay, so now we have these two things, but these two things are just numbers. They are not just matrices, they are inner products, so they are numbers. So what we can do is that we can interchange them without much thought. So I am writing here as psi n0 h prime psi m0. I have written it over here, and this psi m0, oh, sorry, omega psi n0. This I have written over here. So now you see that there is something going on over here. So these are complete set of orthonormal eigenvectors. They are inserted in this way, and you know that they form a complete set. And if you have this kind of things, psi I, let's say, and I starts from 1 to infinite, gives you identity. So these are all possible eigensets. So this is nothing but the orthonormalization of basis set. So you see that if you had psi n0 within this thing, then you would have this psi m0 ket, psi m0 bra, that would be equals to 1, because they form a complete eigenset, but they do not have the psi n0. So what we do is that we allow this summation to run from all possible eigenstates. So this is summation m equals to 1 to infinite, that is all possible values psi n0 h prime psi m0 psi m0 mega psi n0, and we subtract, we add and subtract what we need in order to make it a 1. So and subtract what we have to subtract, we have to subtract the n, right? So this is psi n0 h prime psi n0 and psi n0 omega psi n0. Now you can say that this forms a complete set. So let's say does not involve n. So this is not 1, but this is 1. So this forms a complete basis. So this we can write it as 1. So your sum goes away, and your expression will be psi n0 h prime omega psi n0 minus psi n0 h prime psi n0 multiplied with psi n0 omega psi n0. So you see, we started with a sum which involved all possible eigen functions from m equals to 1 to up to infinity without the n, and now we have only 3 integrations to do for nth state. So for nth state we have to do this integration, the first one, and we have to do 2 integrations for the second part. So your expression, so let's write it, your En2, the correction to the second order energy, now is a compact expression which do not involve a sum. In0 minus in0 in0 Psi 0 omega psi 0. And the only catch is you have to find one such omega so that H prime can be written as a commutator of this omega and H0. So this is the only catch. So now you see your expression, which previously involved a sum and is practically impossible to do if you have almost infinite number of energy eigenstates, now reduces to something which is compact in the sense that you have to do only 3 integrations and you have to subtract from the first part with this first bracket and this second two things. So this is the method in which you can reduce this sum to a finite analytical form. So this method is known as the Dalgarno-Lewis method. So let's write it once more. Dalgarno-Lewis method, which reduces an infinite sum to a which reduces an infinite sum to a compact expression. So this is the trick that you do. So there is no physics involved. So but this is the trick you have to do if you want to find the actual value of this thing. So now I can do it, but probably this will take time, but I can give you something which you can try using this procedure. So let's write it here. So let's say try. So you know that this Hamiltonian for the what is this called? Harmonic oscillator. Harmonic oscillator. So this harmonic oscillator Hamiltonian is nothing but E squared over 2m plus half m omega squared x squared. Now if you have a perturbation, probably this also you have done in your examples or exercise, you have a perturbation such that, let's say, minus q epsilon x. So you have this kind of perturbation such that your now system is given by, so this is H0, so your system is given by H0 plus H prime. So can any of you tell what is the energy that gets shifted due to this kind of perturbation? If any of you can say, then I can write the answer for you so that it will help you find the. So can any of you just answer whether this kind of problem you have faced previously or not while doing the previous this one course? Anyone? Is it too boring to follow or something? Is it too difficult? And anyone just say whether this problem you have done in your previous course while learning quantum mechanics. This one. Anyone please speak up so that I can get a feeling of what is your syllabus regarding the harmonic oscillator and kind of things.
No, sir, we didn't do harmonic oscillator in our previous course.
Huh? You didn't do, but one of your friend just replied that you know that the parity of the harmonic oscillator eigenstates are even odd, and all this. So
Yeah, it was being taught recently in another course.
uh, in
But
other course,
it is taught recently, sir. Harmonic oscillator is in this fifth semester, so it is taught recently. We have not gone through it very clearly.
okay. So you are doing this harmonic oscillator currently, right?
Yes, currently, so not gone through properly,
Yes.
very
So
deeply.
so you know the Hamiltonian for the harmonic oscillator. This is p square by 2m is nothing but half m v square, right?
Yes, yes, we know the Hamiltonian, but this type of problem we never encountered before.
Yes. So what happens is that so let's just give you a context. So this harmonic oscillator, let's say, is nothing but a pendulum, but it is a quantum pendulum, right? So this harmonic. So by the way, so one of you said yesterday that okay. So leave it. So if your harmonic oscillator, which is a classical pendulum, plain classical pendulum that is swinging, it if it is a quantum pendulum, so then that is a harmonic oscillator. So in fancy words, these are quantum harmonic. This one, mm, quantum harmonic oscillators. So you will see certain things that your wave function, there is a finite amount of probability uh, beyond your classical limit, right? This you know, right? So the classical in classical systems, so your harmonic oscillator, let's say your harmonic oscillator moves uh, to a finite distance from the equilibrium, let's say it is plus L, and again goes back to its equilibrium, and for due to the inertia it goes to the other side, and the classical limit of finding the classical region of finding the harmonic oscillator is within minus L to L, right? So this is the classical thing. So of course you see, if you see a pendulum swinging, you know that whatever is the maximum energy, the starting point of the pendulum from any either side of the equilibrium point, you will know that with what, if you do not give any kind of energy to the system will decrease its energy, and in hypothetical condition, which is there is no, if there is no loss of energy, it will be constrained within this minus L to plus L boundary, right? You will not get any kind of pendulum if you place your hand after plus L or before minus L, right? So this is the classical limit. So in quantum systems, as you know, these are described by probabilities. So they have certain finite probability outside this classical region. This thing you have been this one. You have gone through this thing, the existence of
Yes, sir. Yes,
non-pro.
sir.
Yes, so
Yes,
you
sir.
know this.
There is a finite probability beyond the classical limit.
Exactly. So that is only possible due to the quantum nature of this harmonic oscillator.
Yes,
So
sir.
let's say your, yes. So let's say your this Hamiltonian, that is p squared plus 2m plus half m omega squared x squared. This is nothing but k squared x squared. So this harmonic oscillator has some charge. So how it can have this kind of Hamiltonian? So let's say you harmonic oscillator have a charge and you place it some kind of electric field. So if you place it in some kind of electric field, the Hamiltonian that you provide, the Hamiltonian means that you some kind of energy that you provide to the system is nothing but QEX, right? So this is the perturbation that you give to the system in case of charged harmonic oscillator placed in an electric field. So this is a classical problem that you have to face, even if you do this thing. So by the way, can any of you, just for 2-3 minutes discussion, can you say that why do you study harmonic oscillator in so details? So everywhere you face there is a harmonic oscillator. So can any of you tell why the harmonic oscillator is so important that you solve only harmonic oscillator and do nothing other than this harmonic oscillator? So why it is so important about harmonic oscillator? Any of you have gone through this kind of things while encountering this in your current semester? Anything? I mean, why do you solve harmonic oscillator and not nothing else? So probably you must have encountered this infinite square wave and all those kind of. They are also relevant in certain cases, but you see everywhere from probably class 11 you started harmonic oscillator, the spring mass system, right? So what is so special about this harmonic oscillator? Either it is classical or it is quantum. So what is so special about this harmonic oscillator? Have you seen this kind of thing, or anyone can discuss
স্যার
his or her
পোটেনশিয়ালটা একটা স্পেশাল কাইন্ডের।
potential?
পোটেনশিয়ালটা ওই প্যারাবোলা টাইপের, ওই জন্য সব বেশিরভাগ পোটেনশিয়াল যদি এক্সপ্যান্ড করা যায় তাহলে ওরকমই দেখা যায়।
পোটেনশিয়ালটা প্যারাবোলিক ফর্ম হলো, কিন্তু বেশিরভাগ পোটেনশিয়াল মানে কিরকম ধরনের?
মানে এভরি কাইন্ড অফ পোটেনশিয়াল ক্যান বি এক্সপ্রেসড হোয়েন ওই টেলর সিরিজে এক্সপ্লেন করলে তখন দেখা যায় যে সেটা ওই প্যারাবোলা টাইপের, মানে হারমোনিক অসিলেটরের মতনই দেখতে হয়।
হ্যাঁ, কার অ্যাবাউটে?
মানে এই ইকুইলিব্রিয়াম পজিশনের অ্যাবাউটে।
মিনিমার অ্যাবাউটে, তাই তো?
হ্যাঁ স্যার।
So probably all of you know this. So even if you have some kind of unknown potential that you face while solving, so they must have global minimas, and we are interested in this region where there is a global minima or a local minima, and we are interested the region in which the particle is stuck within the equilibrium position and perform certain oscillations. So this is the reason for which you do harmonic oscillator. And as I think, who said this? So Shankar, right? So as he pointed out that every function, every unknown function, let's say you have an fx, and you let's see that your fx has an equilibrium or a global minima about x0, and if you do a Taylor expansion, you will get the you will get a first term which is x minus x0, and you will get a second term which is x minus x0 squared multiplied with the second derivative, and the first term will involve the first derivative. So why you are not interested in the first derivative? Probably all of you know this, but I am just going to
মিনিমাইজার ফোর্সটা তো 0 হয়, ওই জন্য ফার্স্ট ডেরিভেটিভ 0 হয়।
Exactly. So the first derivative is 0. So that is trivial. So the first derivative is 0. So we start with the first non-trivial derivative, which might not be 0. That is the second derivative. And why we do not encounter the fx0, that is the constant part? So what is wrong with the constant part? We do not care what is the constant part, right?
It do not affect the energy eigenvalues.
Of course it affects. So you will see that this affects. So it affects. So probably I just modify your answer. It affects the energy eigenvalue, but it keeps the spectrum fixed. So let's say your energy eigenvalue is 1, 2, 4. So first the gapping is 1, and the second the gapping is 2. Let's say, so let's make some non-trivial values. So let's say your energy eigenvalue is 1, 2, 4, 10. Okay, and the constant part will always add 1 to every one of them, right? So if you have a constant part, so that constant part will be added to every one of them. So it changes the spectrum, of course. So the energy eigenvalues gets changed, but the spectrum, the behavior of the spectrum, the gapping between any two energy eigenvalues, successive energy eigenvalues, they remain fixed. So that is the reason that we do not bother about the energy the constant part in the energy. And in practical situations, we are only interested in the change of energy from one system to another system. We cannot measure, so keep in mind that we cannot measure absolute value of energy of a system. We can only measure what is the change in some certain state to some other state of a system. We cannot measure the absolute value of energy in a system. We are mainly interested, or rather to say, we can measure what is the change in energy. So that's why the constant part we do not care, because that will not shift that will not change any two successive eigenvalues. And the trickiest answer is this harmonic oscillator is the only potential that you can solve analytically. Any other potential, any other slightly complicated potential that you encounter, you cannot get an analytical expression for the solution of this function. But this x squared, which is the quadratic function, this is the only energy I mean, this is the only function that you can solve analytically in terms of potential or Hamiltonian. So can any of you tell what will be the change in energy in this kind of problem? So if you have not gone through this, can any of you just confirm? I can write the value over here. In your current semester in which you are learning this. Anyone? Or you are trying? I don't know. You are trying this right now, or this thing has not yet been taught? You are probably going to learn it probably in this semester also. So can any of you confirm?
H would be H naught plus H prime.
Yes.
Just some over that.
Can you please repeat? So now your harmonic oscillator is little bit, I mean, what to say? So little bit tweaked. So your harmonic oscillator remains same. That is p square by m plus half m omega square x square. But you applied an electric field, and your bob has a charge. So that will.
Sir,
that
the
will,
energy eigenvalue is shifted by a constant only in this case.
yes. So how do you know that?
Sir, like we have the Hamiltonian h plus h prime, and the half m omega square x square minus qex. This can be expressed as a quadratic function of x plus some constant.
Yes. So you know this, right? So why are you not saying this? You know this. So all of you know this thing. What who said? Shovik said, right?
Yes, sir.
Yes. So all of you know this. I am struggling to get your answer. I mean, you I hope you know this, right? Any others can confirm whether you know this trick or not. So you have to make a quadratic out of x squared and x. So that is only possible if it is x. You can somehow take common and I can adjust the x's part and can subtract the x's part and all those kind of things you can do. But you know this trick, right? I mean,
Yes, sir. Yes.
Yes, sir.
so
Yes, sir.
that's why I'm asking. So what is the constant part that you face in this thing? So can any of you just carry out this constant part shift in the energy? So I thought that your quantum mechanics is up to now has not been taught up to harmonic oscillator, but you guys know this, so you should make sure that you tell what you know this, right? So what is this constant part? Any of you can take common and can say what is this extra part? You are doing this, or yes?
Qs square epsilon square by 2m omega square.
Epsilon square by 2m.
2m omega square.
And what is the sign? Plus or minus?
1 minute.
Sir,
it is minus. It is minus.
Yes. So this is the minus. So yes. So this is the shift. So this is the shift in energy. And all of you know that this energy expression for the quantum harmonic oscillator is n plus half h cut omega. This expression you have derived, right?
Yes, sir.
Yes. So you see that so the main goal of doing this thing is that you have done this trick by making a quadratic and have get an analytical form which is exactly correct, right? Q square epsilon square by 2m square. This is an exact form. This is a compact form, analytic solution to the answer of how much change the energy will get after introducing this perturbation. This perturbation is nothing but putting the bulb in an electric field and giving a charge. So you see, you have somehow done this trick and have found out this compact answer. But before that, I have said that this. So let's see. So this q epsilon x. So this epsilon is nothing but the Curly version of E. So I have E for energy. That's why I have written it here epsilon. So let's say you have a correction of QEX. Can somehow intuitively tell what is the first order correction to any eigenstate?
Zero, sir.
So why it is 0? I mentioned it before. So
Sir,
can you
it
just
will
repeat?
Sir, the integrand will become an odd function if it
Yes.
is.
So psi n square, psi n 0 squared is even, right? If it
Yes,
is
yes,
even,
yes.
then it is also even. If it is odd, then it is also even. But you have a linear, so that is q e x q epsilon x. So the overall integrand is nothing but odd, and you integrate from minus infinity to 0. So this is an odd function that gives you 0. So the first order change in the expression for the energy eigenvalue is 0. So now you have to go to the second order, and your second order, if it is non-zero, then it is the basic correction. So you see that whatever value you have come up with, that is the exact value that you have got. And so now I am going to say a situation in front of you. So let's say your second order energy correction gives you exactly this form, minus q square epsilon square by 2m omega square. This form exactly is given by your second order energy correction. What will be your conclusion for the higher order energy correction? Is my question clear? Your first order correction is 0, and let's hope, or let's say that your second order correction you do by any method. You, let's say you use this summation, you do practically infinite number of integrals and add. Even if you have succeeded in doing that, your by this method or by this box, this Dahl-Gardner-Lewis thing, you have come up with the solution, and by chance your solution gives you minus q square epsilon square by 2m omega square. What will be your conclusion for the higher order correction in energy? Let's say third order, fourth order, and something like that. Is my question clear? Let's have a conversation. I mean, don't just keep your
Yes, sir.
muted. Yes. So what will be your conclusion for the higher order energy correction? Your first order is 0. Your second order, by any means you have done integration, adding them up and all those kind of thing. And if you are smart enough, you will do this Dahl-Gardner-Lewis thing, and you find this kind of thing, q minus q square epsilon square and something like that. So someone now tells you, find out the correction for the third order. So my question is, what you will do? You will find out, or you will rely on your physical intuition and say a certain number, or give us some logic. What is the third order correction, or let's say fourth order correction, provided that your second order correction is just the value you have told me, q square epsilon square by 2m omega square.
It will become 0, I think.
No, yes, of course, it will become 0. So you see that.
Sir, it is a quadratic equation. Then the third order, like if we express the potential as a like the Taylor series, then the third differentiation goes to 0.
Third differentiation goes to
It
0.
means that when we expand is a Taylor series,
Which
then
expression?
like the potential expression.
The potential means this half m omega square x squared, right?
Yes.
Yes. Okay.
Then only for the first and I mean the first order automatically 0, because this is equilibrium point. The second order give us a constant value, and then
No. This first order is not the same as expanding it in the Taylor series. So so the argument one of you gave, that we do not bother about the first order because we are looking the bob, or let's say any particle, in the minima or global minima of the about the equilibrium point. So at equilibrium point, whether it is a minima or maxima, the derivative is zero. That's why any kind of Taylor series expansion, if you do about a minima, you will get the first derivative to zero. That has a different answer. But in this case, your first order correction gives you zero by integration only. There is no other possibility or no other no other physical intuition that your first order energy correction is zero. Is there any kind of physical argument that helps you without doing the integration, without doing the even function, odd function? Can you just say by any logic that this will be zero for this? You do the integration, you find it to be zero, right? So by your argument, all of your energy corrections in the problem that you solved previously, the 0.2 to 0.6, that is a constant function, right? So constant function will not have any kind of this derivative only. So by that logic, all of your energy corrections will be zero. But you have found out, right? You have found it out that your first order energy correction is non-zero. Am I clear, Shobhik?
Yes, sir. But the previous case only the first order we get, but the higher order will become zero, right?
How you are so sure about that?
No. I think I wrong.
So let's just check. So you pictorially try to imagine. So you have this thing, right? Psi m0 h prime psi n0. So in your previous problem, h prime is constant, right? H prime is constant, and you can take out of the integral. So is this squared thing, is it zero for 0.2 to 0.6 L?
No, sir, no.
So there is no other argument that you can say that second order correction is zero. It will exist. It will be small, of course, because there is a lambda square in front of en2, right? So it will be smaller than the first order. But you cannot intuitively say that okay, the first order correction is this and the second order correction is zero. It will be, but it will be less important. So where there is a first order non-zero first order thing, we do not go to second order. But so in certain cases we have to go, but we do not go to second order because the first order is dominating. In this case, the first order is zero. So you have to go to the second order. And if it exists, we do not go to any higher orders because we know that the second order dominates over third or fourth. But in this special case, you have seen that by the trick, you probably all of you know that this is a compact answer. And you also know that due to this odd even function trick, your first order correction is zero. And by chance, now if I say that your second order correction gives you this exact value, q square epsilon square by 2m omega square, immediately you can say that you do not have to calculate the third and fourth order, because the logic is that your analytical expression is totally satisfied by the second order expression only. It will do not have any kind of extra parts that you need to correct. The correction in energy that you have done it classically using this quadratic trick, that is pure classical value. So that trick you have done, that is the exact answer. And perturbation is nothing but approximations over approximations, which will help you to reach the exact answer. But in this case, you will find that the second order energy correction, you do it in whichever way you like, you will find that the second order energy correction is this only exactly. And that is the reason behind saying that your higher order correction is exactly zero, because it cannot exceed, right? It cannot exceed. This is an analytical expression.
Sir,
yes.
Sir, we calculate this value by classical trick, but but you say that if we do the second order correction like the Dahl-Gardner-Lewis method or any other method,
Yes.
how can I exactly say that the second order correction gives us this value q square epsilon square by 2m omega square?
So that is your problem that you are going to do.
Yes.
So you find that the second order correction to any energy I can say. So you see there is no n involved. This is important, right? So I am taking so much time in this. There is no n. Your answer, what you have done, involves an n. and this thing whatever you have got q square epsilon square by 2m omega square, there is no n. So in whichever energy eigenstate you calculate, there will be a finite energy correction, and as you said, this is a shift in the energy to every possible energy eigenvalues. So this will not change the difference between two consecutive energy eigenstate, but it will totally shift the spectrum by this value minus q square epsilon square by 2m omega square. But this is a correction, and you will find that if you do any of this trick, either Dalgarno-Lewis or this thing, this box thing, which is probably impossible to calculate for infinite number of energy eigenstates, you will find that your second order energy expression for any n, En, let's say you have En2, if you calculate this thing, you will find that your energy expression will be exactly minus q square epsilon square by 2m omega square. That I guarantee you that will happen. So you have to do this. So
Okay, sir.
okay. So this I am not doing, but this you have to do it. So then you will see that the second order energy correction gives you exactly this value. And the important thing is that there is no n involved. So you can take any eigenfunction or any energy eigenvalue, whichever is simpler to you. Okay, so that is the importance of this trick. Probably, so you do this. Okay, so you try to do this. If you do not have time, then it is okay, but you try to do this using any trick. Probably your Dalgarno-Lewis will help you. So first your expression, so the approach to do this thing is first to find this omega. So this omega can be find out from this commutation relation, psi h prime equals to commutator of omega and h naught, and you apply. So this is the equation, and you apply any psi n with whatever psi n you like, any psi n on both sides, and do the derivative. Okay, as you know that your expression will not depend on n, so any psi n you take, you multiply on both sides and you do the derivative. So where the derivative involves, you see that h prime is q epsilon x and h0 is p squared. So the p squared is nothing but ih cut minus ih cut del del x. So that will remove the derivative, and omega is also a function. So you will have, so this omega h0 commutator will have what? Omega h0 minus h0 omega. So h0 will involve a derivative. So the first thing, whenever there is h0 omega and you apply it on some wave function, so you have to derivate omega also and x also, right? The way eigenstate also. So you do this, you will find that this thing exactly comes out to be q square epsilon square by 2m omega square. Okay. So up to now, did you face any kind of difficulty, or I have to repeat this? I spend a lot of time. So is this clear? What we are doing till now, either this Dalgarno-Lewis method or anything related to whatever we have done today? I have very little time, but I will try to finish one thing which will help me to continue from tomorrow. So is it clear to all of you what I am doing? Is there anything we need to discuss more related to this Dalgarno-Lewis or perturbation in general?
So we have to go through the notes once again.
Oh, no. So see this if you write it down and if you multiply it with psi n 0, you will eventually get whatever I have got. There is nothing. So see, 3, 4, 5, 6 line step. I have explicitly written it here because of course this is online and I have to do this thing explicitly. That's why. So this is very much trivial. So if you so the main thing is that which is in green, if you can find, so that is the catch over here. The trickiest part is finding this omega in practical situation with the problem I have given over here. The rest is only pure algebra. You have to split it in terms of this. Any other conceptual difficulty you are facing while digesting this? Of course, I will update with the notes, but any other conceptual difficulty you want to discuss right now, or we can move further with just one small step. I am already overshooting your time, but can I proceed, or
Sir,
you need to discuss?
sir, actually we have a college meeting today at 6:10 p.m.
So you should have told me previously, no? That you have a college meeting. I do not mind whether you have a meeting or not, but I spent so much time just to make sure. Okay, so So it will be easier for you if I start if I end this meeting slightly before the usual time, right? So is that your you all of you are interested in? Is it favorable for you? I mean, this situation, if I end it, so I have completed one section, and now I will apply whatever I have done this to an actual harder problem, which is the hydrogen atom. So these are harder in a sense that they are calculatively harder. They are not physically harder. They are calculatively harder, and you have to interpret the results. Whatever you have, so probably you have heard while learning chemistry in 11, 12 that if you apply magnetic field, your L level splits up, your M level splits up. All those things you have heard, right? So, but whatever we have seen here that the energy eigenvalue of the hydrogen atom depends only on N. The thing which Tirthu sir was talking about, this is something non-trivial, that after doing all of this your energy eigenvalue depends on N. So this has much deeper implication, but you will see that even after applying perturbation you can split the energy levels that probably you have already known that so you have probably heard about this SPDF and all those kind of things which you learn in chemistry in 11 or 12. So you will see that if you apply perturbation or if you apply external effects to your system, your energy level splits up, and splitting up means your energy level which depends only on N now will not depend on N now, it will involve some other things. So that we are doing, we will do in this next thing, I mean using perturbation. So that is that. So I have developed the machinery over here, so I will only use some of the boxes today I have written while doing the hydrogen atom, and the calculation will be heavier comparatively, because of course you know that is the hydrogen atom, it is a basic thing in the, I mean basic molecule that exists.
We still have 20 minutes about
20. So you said that it is in 6:10, right?
around 6:15, 6:10, 6:15. We can be 5 minutes late.
Okay. So you can be 5 minutes late. So let's set up the stage for tomorrow, and then so 15 would be difficult, but okay. So let's set up the stage for tomorrow. Okay, that's why. So if you have told me previously, then I can discuss all these things later. I spent so much time. Okay, fine. So don't mess with these calculations. Okay, so don't mess around this calculation. You do it once, and you keep it in a separate copy which you will use for later purpose. I am also doing that. Okay, so this hydrogen atom, what I am writing, so this hydrogen atom, I will not take much of your time. Hydrogen atom. So see, so hydrogen atom, we have said from the first day only that this hydrogen atom is extremely lonely, right? It is lonely in this entire universe, that there is no other hydrogen atom or any other thing that can change the Coulomb potential, which is absolutely rubbish, because you have very much perturbation in this entire in your separated labs only, right? So you do not have perturbations or any kind of additional effects in your itself BSc lab, whatever you have done, which alter your result. But you see that this hydrogen atom we have solved, this is absolutely hypothetical. So there are many more corrections. So I am writing down whatever we have neglected, and whatever we have neglected, we will try to incorporate this as a perturbation. Okay, so that is our usual plan. So we neglected, I mean we just overlooked, this is the reduced mass correction, which we probably discussed. Reduced mass correction. So we I think Sir probably mentioned that this two body problem can be reduced to an one body problem if you go into the center of mass. So whatever we written here M, which is the electron mass, we will reduce with this mu, where mu is nothing but the this one me mp by me plus mp, right? So this is the reduced mass. So this is the first thing we neglected, and we just, this is nothing trivial. We have to replace all the m by mu. So this, that is not so much important. Yes, and then we are doing this fine structure. So this is the important part. So this is the fine structure, and I will explain this what is fine structure, and then there is the hyperfine structure. Hyperfine structure. So this fine structure is combined of two things. First, there is a relativistic correction. We have to take into account the relativistic correction to the energy of the electron, or the speed at which the electron moves. If it is too much relativistic, then we have to take the relativistic correction, which is true, as you know, that in analogy with the planets, if it has an elliptical orbit, it moves fast to the edge where it is the closest, right? So you have done this Kepler thing, Kepler body, Kepler planet motion. So if you have elliptical orbits, and if your planet is revolving in that orbit, and you have sun in the middle, the shortest time it takes while passing through the orbital circumference is closest to the sun, right? Yeah, you know this. I mean,
Yes, sir.
Yes, sir.
so you know this, okay. So in that case, there should be a correction in the speed, and we need to take this into account using the relativistic correction. And another thing is the spin orbit coupling. So this was introduced, I mean, this was, I think probably one of you mentioned, this spin orbit coupling is nothing but so this is actually involving the angular momentum transformation, right? So this angular momentum, which is the orbital angular momentum, gets coupled with the spin angular momentum with the s. So the orbital angular momentum L gets coupled with the spin orbital momentum, which involves an s, and they are coupled. So they have two possibilities of coupling. So probably you know this term, LS and JJ coupling. So these two are coupled in a way, so they need some this correction to the angular part. Previously we have solved the angular part separately, right? You have seen that we use the separation of variables, and we have totally separated out the angular part apart from the radial part, and we got the solutions as spherical harmonics. Now this needs a correction. This needs the correction from the spin part. And we know that electrons are fermions, they have spins, they are half integer spins, and they get sometimes coupled. So the orbital angular part needs correction from the spin part, and this is the spin orbit coupling. And this hyperfine structure is little bit non-trivial. So this is the spin-spins coupling. So this is the spin-spin interaction. So can anyone guess what is the spin? Why there are two spins? Please answer quickly, because you have to leave, right? If you
No,
want
sir.
to, yes. So can anyone guess why there is a two spin? I mean, spin. So
Up spin and down spin, two type of.
so electron has only one spin. Either it is in the up spin state or it is in the down spin state. So there is no up and down simultaneously present, right? Because there is only one electron. Hydrogen atom is the simplest possible molecule. Sorry, atom. So that has only one electron. So there is no up and down. If it is down, it remains down. If it is up, it remains up. But there is only one electron, right? So this second spin is nothing but the spin of the proton, which we do not care about previously. So this proton is also a fermion, right? So this fermion, I mean, of course, is a composite particle, but it is a fermion, right? It has spins. So it has half integer. It is treated as a composite fermion, and it has a spin, and it is also half. So the spin-spin interaction also you have to take into account. And these are the intrinsic perturbations present within the hydrogen atom without any kind of external magnetic or electric field. So these three things. So first one is the reduced mass correction. Okay. So reduced mass correction. This exists within the hydrogen atom. we just replace m by mu, nothing more than that. And there is a fine structure, it is present within the hydrogen atom, but we have not explicitly taken care of while solving the differential equation of the Schrodinger equation. And there is even more much integrated contribution coming from the spins of electron and this proton spin. So they have a spin-spin interaction. And then you have external things. The external thing is that, let's say you know this, these are Zeeman effect. So this Zeeman effect is nothing but putting an hydrogen atom plus external B field, this is magnetic field, and then you have the Stark effect. So Stark effect of various kinds, I will not go into that, but Stark effect, this is hydrogen atom placed in an electric field. So these are the possible all kinds of possible perturbations that you can possible. So these are external. Last two things, Zeeman and Stark, these are external, and the first three is more severe because they are present, but we have not taken into account while solving this. So we have to do this fine structure, which consists of two parts, relativistic correction and the spin orbit coupling, which will be spin orbit coupling and the hyperfine structure. Probably I will try able to complete this fine structure and hyperfine tomorrow. I hope. So by the way, tomorrow you have this meeting from 6:15 or any other time?
Sir, only no, sir, only today.
So tomorrow I can take up to, let's say, 6:15.
Yes, sir. No problem.
Okay. So no problem. Okay, fine. So probably I will exceed up to 15 to 20 minutes. I will not push further, but I will take let's say 15 to 20 minutes extra if I cannot complete. But I hope I can finish fine structure and hyperfine structure tomorrow. So I will start with the fine structure with the relativistic correction tomorrow, and I will somehow speed things up. So if you have some conceptual difficulty, you please stop me, then we can discuss. And if the calculation is not understandable at that point of time, so you can always go through this afterwards and you can mention where if I have made any kind of mistake or not. Probably I will not do this kind of anything, but if I make some factors wrong, you can always point it out afterwards. So I will just try to speed things up. You just grasp the concepts while doing this 1.5 or 2 hours long this session, but you just grasp the concepts, and I will slightly speed things up. Okay, so it is already 6:06, so we will so let's end this meeting today. We will meet tomorrow. You will also have to leave for the group meeting, and tomorrow I will start at 4:30 dot. Okay, so is it fine to all of you, or
Yes, sir.
anything you want to discuss? I will forward this note to you, and if you get time today or any time in so probably you have other things to do also, but if you get some time, try this. Okay, so this is nothing but doing quantum mechanics in a harder way using the Dalton-Lewis method. But you see, if this doesn't exist, you have trouble, right? So all the things do not have analytical solutions. This trick, x square and quadratic thing, that trick, this doesn't work all the time. But this is actually testing easier problems in a harder manner. So probably I end this meeting now. I am overshooted, so I do not want to overshoot more. So probably we can meet at 4:30. So please be on time. Try to be on time if you don't have other engagements. I will start at 4:30 tomorrow. Okay.
Okay, sir.
Okay, fine. I am ending this session right now.
Okay, sir.